Hello student, in a previous lecture we have studied what is meant by the buoyancy and also the center of buoyancy. We have solved many problems on the same. Now in this lecture we are going to study the metacenter and the metacentric height. Okay, so first we will start with the metacenter. Metacenter is defined as the point about which the body starts oscillating when the body is tilted by a small angle. Okay, when there is the body is tilted, that time. In the figure you can see the some body is floating over the water, and then it is tilted. In a second figure you can see this body is tilted and by some amount due to the angular displacement. Okay, so here the point M indicating the metacenter. It is the intersection of this normal axis and also the line of action of the force of buoyancy. So the metacenter may also be defined as the point at which the line of action of the force of buoyancy will meet the normal axis of the body when the body is given a small angular displacement. Okay, so first consider the body which is floating over the liquid. Okay, so it is in the equilibrium condition. So G indicates the center of gravity and B indicates the center of buoyancy. So when it is floating over the water, the center of buoyancy and the center of gravity is acting on a normal axis. Okay, because it is in the equilibrium condition. Okay, when this body when an angular displacement is given to the body, okay, what will happen, the body is tilted, okay, by this and due to this angular displacement. Okay, and um, and then due to this angular displacement the force of buoyancy, that is the point B, is the force of buoyancy is changes from B to B1 because it is tilted. Okay, so because of this then if we draw the line of action from the from this point B1, then what will happen, this line of action of this force of buoyancy now will meet the when meets the normal axis. Okay, then the point uh, uh, is called, this point, the intersection point is called as a metacenter. Okay, so the definition is the so we can define the intersection of the normal axis and also the force of beyond and the line of action of this force of buoyancy. Okay, so due to this angular displacement, the force of buoyancy is shifted from B to B1. Okay, and this is the line of action. This line of action of this force of buoyancy is meeting the normal axis at this point. This point is nothing but the metacenter. Okay, now we will see what is the metacentric height. Metacentric height is the distance in G, that is a distance between the metacenter of a floating body and the center of gravity of the body. It's called as a center metacentric height. In the figure you can see the distance in G is nothing but the metacentric height, the distance between the center of gravity and also the metacenter is nothing with the metacentric height. Okay, so here the distance gm indicating the metacentric height. Okay, now we will see how to measure this height. Okay, so we will derive the expression for this metacentric height. Okay, so analytical method for the metacentric height. Then consider this is a body. Okay, figure 4.a showing the position of the floating body in the equilibrium. So this is a body which is floating in a water and it is in the equilibrium. So G is indicating the center of gravity and B is indicating the center of buoyancy. Okay. Then the floating body is given a small angular displacement in the clockwise direction. Okay, if we have applied some force on this, okay, on the right side of this body, that is the angular displacement is given to the body, then this body starts oscillating and it is tilted, okay, in the right side direction. In the figure B you can see this is a this body is tilted, okay. The new center of buoyancy, so it is tilted in the clockwise direction. Angular displacement is given on the right side of this figure, right side of this body, and due to this the body is tilted by some amount. As the body is tilted, the force of buoyancy is also um, shifted from B to B1. Okay, so the vertical line through the B1 cuts the normal axis at the point A. Okay, and then this M is nothing but the metacentric height. Okay, then we have to find out the distance GM, that is the center, that is the distance between the center of gravity uh, and also the metacenter. Okay, so this is the metacentric height that we have to calculate. Okay, so up to this we have seen that the body is tilted by the some angular displacement, then the due to this angular displacement the force of buoyancy changes from B to B1. Okay, if we draw the line of action of this through this B1, or we can, then this line of action is meeting the normal axis at the point A, which is called as a metacenter. Then we have to measure the distance between the GM, means the metacentric height is the distance between the center of gravity and also the point M, that is the metacenter. Okay, for this consider due to this angular displacement of the body in the clockwise direction, it causes a wedge shaped prism, that is here in the figure you can see a wedge shaped prism is there, BOB. Okay, and also on the left side of this also there is another prism, wedge shaped prism, that is A dash. Okay, in the so this wedge shaped prism on the right side is inside the water. Okay, on the left side the wedge shaped prism is A dash, which is emerging out from the water. Okay, so this wedge is showing what the gain of buoyancy at the right side. Okay, and the loss of buoyancy in the left side. So the dF is the force in the figure. This wedges represent the gain of gain of the force on the right side, and also corresponding loss of beyond force on the left side. Okay, the gain is represented by a vertical force. In the figure you can see dF is there. Okay, so on a right side the force of buoyancy, there is a gain in the force of buoyancy, so this dF is acting vertically upward. Okay, and in the prism OA dash, the force dF is acting downward, because this wedge shaped prism is emerges out from the liquid. Okay, so this df is acting downwards. Then this look into these two forces df and df1. So these are also um, um, mm, preparing a couple. Okay, due to these two forces also the couple is there. Okay, but here the angular displacement is in the counterclockwise direction. Okay, so here from df here to here, so this display the moment is the couple is in the counterclockwise direction. Okay, then um, we have uh, then we have to find out the this value this the couple due to this buoyancy force df tends to rotate the ship in the counterclockwise direction. These two forces df, okay, making the counterclockwise couple. So this couple due to this buoyancy force df tends to rotate the ship in the counterclockwise direction. Okay, also the moment caused by the displacement of the center of buoyancy from b to b1 is also in the counterclockwise direction. Okay, in the figure you can see the moment which is caused by the due to the shifting of this force of buoyancy from b to b1. And okay, so here there is another moment. Okay, and this moment is also the couple is also there. This couple is also in the counterclockwise direction. Okay, that is from here to here. So this we get the two counterclockwise couples due to this force df, and also due to the b and b dash, that is the displacement of the center of buoyancy. Okay, so these two counterclockwise movements should be of equal. Okay, okay, thus these two couples must be of equal, both are in the counterclockwise direction. So first we will calculate the couple due to the wedges. Okay, then consider towards the right side of the axis a small streak of thickness dx at a distance x from the O. Okay, here here in the prism of a BOB dash we have considered a small strip which is and the thickness is dx. So over here the consider a one strip. Okay, so this strip is at the distance of x from here to here. So here we are considering the a small strip on the right side. Okay, and the thickness of this is dx. This strip is at the distance x from the O. Okay, in the plan you can also see the thickness is dx and it is a distance x from the O. Okay, then the height of this strip is equal to what? X, that is the distance, into the angle BOB. Okay, this here the angle BOB dash in the figure, angle BOB dash is equal to angle AOA dash, and also it is equal to BMB1. Okay, and all this is equal to what? Theta. All three angles are equal and it is equal to theta. So the distance then the height of the strip is equal to what? X into angle BOB. Okay, that is x into theta. Okay, then we get the height of this strip. Then we are the area of the strip is equal to what? Height into the thickness. We already know the thickness is dx. Okay, we have calculated the height which is x into theta. So the area of the strip is x into theta into the dx. Okay, now if the length L is the length of this floating body, then the volume of the strip is, volume is nothing but the area into the length. Okay, so um, the area is what, we have calculated x into theta into dx. Okay, so x in area into L, this x into theta into the L into dx, this is the volume of the strip. Okay, L is the length of the floating body. You can see this is the, we are considering this strip. Okay, the length of this so and in the this floating body is having a length is L. Okay, so the area of that the volume of the strip is equal to area into L, that is x into theta into L into dx. Okay, this is the volume of the strip. Okay, then we have to calculate the weight of the strip. Okay, weight is nothing but the density into acceleration due to gravity into the volume. Okay, then which is equal to rho g, volume is x theta L dx. Okay, so we get the value of weight of the strip, which is equal to rho g x theta L dx. Okay, so we are considering this weight of the strip, we are considering the strip on the left side of the axis. Okay, which is at a distance x from the point O. If we consider the same strip on the right, we are considering the strip on the left side. Okay, if the same if we consider the same strip on the right side, then the weight of the strip is similar to the weight of the strip on the right side, which is equal to rho g is equal to rho g x theta L dx. Okay, on the left side also, on the right side also, and the weight of the strip is rho g x theta L dx. Okay, then these two weights are acting in the opposite direction, hence they constitute a couple. Okay, here these these two weights are acting in opposite direction, and okay, because this part is in the liquid and this part is about emerging out from the liquid, so the weight of these two is also in the opposite direction. So they are also due to these two weights, they constitute a couple. Okay, so the moment due to this couple is equal to what, weight of the each strip into the distance between these two weights, which is equal to weight of the each strip is rho g x theta L dx. Okay, and distance between these two is x plus x, because x is the distance um, from the strip up to the O. Okay, and if we are considering the strip on the both side, okay, so this distance is double, that is x plus x. Okay, that is x plus x means the distance between these two weights. Okay, then if we multiply all this, we get the value of moment of this couple is equal to 2 rho g x theta L dx. Okay, then moment of this couple, we get the value of this. Then if we consider the whole wedge, then the moment of the couple for the whole wedge is the integration of this term, that is the integration of 2 rho g x theta L dx. Okay, this is our first equation, that is moment of the couple due to the whole wedge. Okay, then this couple is equal to the couple which is formed due to the center of buoyancy from B to B1. Okay, So the moment of the couple due to the shifting of the center of buoyancy from B to B1 is equal to what? The force of buoyancy into the distance B into B1. In the figure you can see. So here the B is shifted over the here, and due to the shifting the couple is there in the clock and counterclockwise direction. Okay, so how to calculate this? The couple is equal to moment into force into the distance. So force is over here is buoyancy force, that is a B, and distance is B to B1. Okay, so the couple moment of the couple due to the shifting of the center of buoyancy from B to B1 is equal to AB into BB1. Okay, but BB1 is equal to what? BM into theta, because the theta is very small. Okay, so we can written as AB into BM into theta. But also we know that the force of buoyancy is equal to the weight of this body. Okay, W. The force of buoyancy is equal to the weight of the body. So we can also written as, that is AB is equal to W. So we can also be written as W into BM into theta is equal to the moment of couple due to the shifting of the center of buoyancy from B to B1. Okay, so this is our second equation. If we so these two couples are in a and counterclockwise direction, these two couples must be same, are the same. So we have to equate this two equation. So by equating this we get W into BM into theta is equal to integration of 2 rho g x square theta L dx. Okay, so in the figure, so 2 rho g theta is comes out from integration, and which is and remaining term is integration of x square L dx. Okay, so theta and theta is cancelled out from both the sides. Then we get W into BM is equal to 2 rho g into integration of x square L dx. Okay, then this L dx is the experimental area on the water line. Okay, and which is equal to the dA. Okay, now put this value of L dx into the above equation. We get W into Bm is equal to 2 rho g integration of x square L dx is dA. So integration of x square dA. Okay, but from the figure it is clear that integration of x square 2 times x square dA is the second moment of the area of the plane of the body at the water surface about the axis yy. So it is equal to r is equal to that is 2 integration of x square dA is equal to r. Okay, this is the second moment of area of the plane of the body at the water surface about the axis yy, so which is equal to r. So this can we also be written as W into Bm is equal to rho g I. Okay, then Bm is equal to rho g I upon W. Okay, so then we have to calculate the value of W, that is the weight of the body. We know that weight of the body is nothing but the weight of the fluid displaced by the body. Okay, how to calculate this? Weight of the fluid displaced in the body is equal to rho g into the volume of the fluid displaced by the body. Okay, so rho g into the volume of the body submerged in the water. Okay, which is written as by this is showing the symbol showing the volume of the body submerged in the water. So W is equal to rho G into V. Okay. Uh, then Bm is equal to rho Gr into rho G V. Okay. So rho G and rho G are cancel out. So it is equal to I upon V. That is the volume of the body submerged in the water. Then Gm is equal, so we get the value of Bm, but we know that the Gm, that is the metacentric height, is equal to what? Bm minus Bg. So look into this figure. We have to calculate the Gm. So B, from B to M minus Bg, then we get the value of Mg, that is our Gm. So that is the metacentric height. So Bm minus Bg is equal to Gm. Okay. Then put the value of, we have calculated the value of Bm. So put this value into the equation, which is 1 upon B minus Bg. Okay. So we get the value of metacentric height is equal to I, that is moment of inertia upon the volume of the body submerged in the water minus the value of Bg. Okay, this is the metacentric height. Hope we have understand how to find out the metacentric height. Okay, then we will see now the problems on the same. The problem is a rectangular pontoon is 5 meter long, 3 meter wide, 1.2 meter high. Okay, the depth of the immersion of the pontoon is 0.80 meter in seawater. If the center of the gravity is 0.6 meter above the bottom of the pontoon, determine the metacentric height. The density of the water is 1025 kilogram per meter cube. Okay, so what they have given in the example is, they have given the dimension of the pontoon, which is 5 meter long, 3 meter wide, 1.2 meter high. Okay, and also they have given the depth of the immersion, which is 0.8 meter. Also the and the density of seawater is 1025 and the center of gravity is 1.6 meter above the bottom of the pontoon. Okay, so here is the figure, okay, which is showing the dimensions. Okay. The width is 3 meter, height is 1.2 meter, and length is 3 meter. Okay. Also, they have given that the depth of immersion is 0.8. So here I am showing the height 8. Okay. Now to show the position of the center of gravity and the center of buoyancy. If the height is 1.2, then the center of gravity will acting at the center of this 1.2. Okay, that is at the distance of 0.6. Okay, so from A to G the distance is 0.6 meter. Okay, then B means the center of the buoyancy, that is the center of the portion of the body which is immersed or the submerged in the water. Okay, so here point is 8 is the depth of the immersion, and the half part on the center of buoyancy will act at the center of this height. So it is equal to 1 upon 2 into the depth of the immersion. So distance A to B is equal to 1 upon 2 into 0.8, that is 0.4. From A to B the distance is 0.4. Okay. Then they have already given in the example is the density of the seawater is 1025 kilogram per meter cube. Okay, which is not needed anywhere. Okay, so we have to calculate the metacentric height. We know that is we have to calculate the value of gm. Okay, so gm is equal to I upon volume of the body submerged in the water minus Vg. Okay, so first we have to calculate the I, that is moment of inertia of the plane of the quantum about this y axis, that is a vertical axis. So here I is equal to as it is in rectangular, so it is 1 upon 12 bd cube, that is bd cube by 12. So it is equal to 1 upon 12 into b is 5, d is 3, cube into meter raised to 4 is equal to 45 by 4 meter raised to 4. We get the value of I as 45 by 4 meter raised to 4. Okay, I is bh cube by 12. Then we have to calculate the volume of the body submerged in the water, which is equal to, so here the which is volume of the body submerged in the water. They have already given the is the dimension, which is breadth is 3, then height is 0.8 and the length is 5 meter. Okay, so which is equal to 12 meter cube. The volume of the body submerged in the water is equal to 12 meter cube. Then bg, from b to g we have to calculate the distance bg. So in the figure you can see ag minus ab, then we get the value of bg. We know the value of ag, it is 0.6, ab it is 0.4. so by subtracting in this 0.6 minus 0.2, we get the value of b to g, okay, which is equal to 0.2 meter. Okay, then gm is equal to I upon volume of the water submerged in the liquid minus Vg. So it is equal to 45 by 4 into 12 into 1 upon 12 minus 0.2. So gm is equal to, okay, after calculating this we get the value of gm is 0.7375 meter. Okay, so this is the answer of our problem, the value of the gm. Okay, now we will see one more problem in the figure. So here we have in the first example we have seen the rectangular shape is immersed into the liquid. Now we will see circular body immersed in the liquid. So here the problem statement is a uniform body of size 3 meter long. Okay, so here 3 meter long, 2 meter wide, 2 meter wide and 1 meter deep, floats in a water. What is the weight of the body if the depth of immersion is 0.8 meter? Determine the metacentric height also. So what we have to calculate is the weight of the body, then the metacentric height. Okay, so what they have given in the example, the dimension of the body is 2 meter long, 2 meter wide and 1 meter deep. So okay, then the depth of immersion is also they have given 0.8 meter. Find what weight of the body, that is W we have to calculate. Then so the metacentric height, that is gm. Okay, So first we'll start with the we will find out the weight of the body. Weight of the body is equal to what? Weight of the water displayed. Okay, so it is equal to rho g into the volume of the water displayed. Rho is 1000, g is 9.81 into the volume of the body displayed, as they have already given us the volume, the dimensions, length, breadth into height. So it is equal to 1000 into 9.81 into 3 into 2 into 0.8 Newton. So by multiplying all these terms, we get the final value of weight of the body as 47088 Newton. Okay, and then now we have to calculate the metacentric height, that is GM. So GM formula is I upon volume of the body submerged in the water and minus Vg. We have to calculate first the I, that is the moment of the inertia. Moment of inertia about the y axis of the plant body. So which is equal to 1 upon 12 dh cube. Okay, so it is by putting this we get 2 meter raised to 4 value of the I. Then we have to calculate the volume of the body in the water. Okay, so here volume of the body in water is, which is submerged in the water. Okay, they have already given the length is 3 width is 2 meter long, then 2 meter wide. Okay, they have given then, but here 1 meter deep is in the water, but the submerged part is 0.8 meter. So the volume of the body in water is equal to 3 into 2 into the height, that is the part of the body which is immersed in the water, which is equal to 0.8. So by multiplying this, we get the value of volume of the body in water as 4.8 meter cube. Okay, now the formula for the Vg is Ag minus Ab. In the figure you can see here the Bg is Ag minus Ab. So here Ag is the A to G, is the distance from here to here. Okay, so which is equal to Ag is 1 by 2 minus 0.8 by 2. Okay, so they have given it is 1 meter deep. The body is 1 meter deep. So the center of gravity will acting at the half of this. Okay, then that is G m. So 1 by 2 minus the height, and the center of buoyancy is acting at the distance of half and the height h by 2. The height is 0.8, so it is 0.8 by 2. The distance between these two is nothing but the Bg, which is equal to 0.1. Okay, then the Gm is equal to what? Gm is equal to I upon volume of the body submerged in the liquid minus the value of Bg. So by putting this value, we get the value of Gm as 0.3167 meter. Okay, now we will see the another problem. A block of the wood of specific gravity is 0.7 in water. Determine the metacentric height of the block if its size is through 2 meter into 1 meter into 0.8. Okay, so then first is the dimension they have already given, which is equal to 2 into 1 into 0.8. Okay, depth of immersion Hmm, they have given in the they have not given, so we are considering the depth of the immersion as 8 meter. Okay, they have already given the specific gravity of the wood, which is 0.7. And okay, so first we have to calculate the weight of the wooden piece. Weight of the wooden piece is equal to weight density of the wood into the volume. Weight density of wood is equal to 0.7 into the density of water into the g, that is weight W is equal to rho g. Rho is here 0.7 into 1000, g is 9.81 into the volume. Volume is 2 into 1 into 0.8. 2 into 1 into 0.8. So this is the value of weight of the wooden piece. Okay, but the weight of the water displaced is equal to weight density of the water into the volume of the wood submerged in the water. Here, so weight density of water is rho into g. So 1000 into 9.81 into the volume of the wood submerged in the water. So here 2 meter into 1 meter into, we don't know the height of immersion, so we are considering the depth of immersion is 8. So here the weight of the water displaced is equal to 1000 into 9.81 into 2 into 1 into 8. Okay, next for the equilibrium, weight of this wooden piece is equal to what? Weight of the water displayed. Okay. When this body is immersed in a liquid, then the weight of this wooden piece is the water is displayed, and the weight of this water displayed is equal to the weight of this wooden piece. Okay, so by equating these two, we will get the value of H as okay 0.7 into 40, that is 0.56 meters. Okay, by multiplying all these, calculating this, we get the value of H as 0.56 meter. Okay, that is the height of immersion we have. We get is the 0.56 meter. Okay, so height of this wooden block is 0.2 and the height of the immersion is 0.56 meter. We have to calculate the distance gm. Okay, for that first we have to calculate the value of ag. Ag means the ag, the height. G is the center of the gravity. Okay, it is acting half of this height of the wooden block, which is equal to it is equal to what? 0.8 by 2, which is 4 meter. And A to B, that is B indicating the force of B on C, B indicating the center of B on C, which means the half of the part of the depth of the water immersed in the depth of this wooden block immersed in the liquid. So height is here 0.6 we have calculated. So half of this is equal to the distance AB, which is equal to 0.28 meter. Okay, if we subtract we have to calculate the distance B to G. Okay, we know that the value of AG, which is 0.4, then AB, which is AB, it is 0.28. So by subtracting this, we get value of BG is equal to 0.12 meter. Okay, then the metacentric height is, the formula for the metacentric height is I upon volume of the water submerged in the liquid, volume of the body submerged in the water, minus Bg. Okay, so first we have to calculate the I, and this is the moment of inertia about the axis y, so which is equal to 1:6 meter to 4. Okay, then the volume is then we have to calculate the volume of the wood in the water, so it is equal to 2 into 1. Height is the height of the body which is submerged in the water. Okay, so 2 into 1 into 0.26. So we get the volume of the wood in water is 1.12 meter cube. Okay, so put all this value into the formula of GM, that is the metacentric height, is equal to I is 1:6 upon volume of the body submerged, volume of the wood in water, which is into 1.1.12 minus the Bg, which is 0.12. Okay, so by calculating this, we get the value of GM as 0.0288 meter. Okay. Now we will see one more problem. Okay, so here a cylinder, a solid cylinder uh, of diameter 4 meters has a height of 3 meter. Okay, and the metacentric height of the cylinder when it is floating in water with its vertical axis. The specific gravity of the cylinder is 0.6. So what they have given in the example is the diameter of the cylinder is 4 meter and the height of the cylinder is 3 meter. Okay, we have to calculate the metacentric height. Specific gravity of the cylinder they have already given. So specific gravity is 0.6. Then the depth of immersion of the cylinder is 0.6 into 3, which is equal to 1.8. Okay, so we get the depth of the immersion, which is 1.8. In the figure you can see the diameter is 4 meter and it is the height of that cylinder, the depth of the cylinder is, that is the height of that cylinder is 3 meter. Okay, and then the center of gravity will acting over here, which is the half part of this 3 meter. Okay, so distance AG is half of this height of the that is the depth of this cylindrical body, which is 3 meter. So 3 by 2 is 1.5 meter. Distance AG is 1.5 meter. Depth of the immersion we have found out as 1.8. So distance AB is half of this distance of the immersion of this cylinder, which is equal to 0.9 meter. So AB is 0.9 meter into G is 1.5 meter. We can calculate the BG, AG minus AB. So it is equal to 0.6 meter. Now the metacentric height formula is I upon volume of the water submerged, volume of the body submerged in the water minus Bg. First we have to calculate the I value. I is the moment of inertia about the axis y of the plane of the body. So it is equal to, as it is in circle, so it is equal to pi by 64 d raised to 4. Okay, so pi by 64, here the diameter is 4 meter. Okay, so it is equal to pi by 64 into 4 raised to 4. Okay, then I is the volume of the cylinder in water. Okay, volume means the area into the depth of immersion. So area is pi by 4 d square, that is pi by 4 into 4 square into depth of immersion is 1.8. So which is equal to GM is equal to pi by 64 into 4 raised to 4 upon pi by 4 into 4 square into 1.8 minus Bg, the value of Bg is 0.6. Okay, so after calculating all these terms we get the value of GM as minus 0.05 meter. So here the value of GM is in minus. So here minus sign means the metacenter is below the center of the gravity. Okay, in the figure you can see the here the value of m. The m is below the center of gravity, so it should be at a distance. It is it should be over here somewhere. That is, it is from near is it is below the center of the gravity. Hope you have understand all these problems on this metacentric height, how to calculate the metacentric height. Okay, so we will now stop over here. Thank you.